Hello everyone. We are going to discuss about Prim's algorithm. In the previous sessions we looked at the concept of spanning tree followed by the idea of minimum spanning tree, and then we also looked at the Kruskal's algorithm to generate a minimum spanning tree for a given graph. Now in this session we are going to discuss about the Prim's algorithm, another very popular approach which is used to generate minimum spanning tree for a given graph. So the objective of this session is to define the Prim's algorithm. The sequence of steps have to be defined, followed by an understanding of the algorithm with an example. So we take a graph and then we go through the steps of the algorithm to understand how it works, how it generates a minimum spanning tree. Then we look at the time complexity part, and finally we'll conclude with an implementation of it. And the reference is given below here, so you can have a look at it to understand more details of this particular algorithm. So what did we look at so far? So we looked at the idea of spanning tree and minimum spanning tree. Minimum spanning tree is essentially one spanning tree of a given weighted graph with least cost, and more than one minimum spanning tree may also exist, that we already discussed. And we also looked at the Kruskal's algorithm to generate the MST. As discussed in the beginning of the session, the next algorithm that we are going to look at is Prim's algorithm. So Prim's algorithm is also a greedy algorithm. Just like Kruskal's algorithm, it also uses a greedy approach. Why is it greedy? It also picks the least weighted edge among all the available edges. So that's why it is greedy. So if you look at the approach, the first step is just like Kruskal's algorithm. The first step is to remove all the loops and parallel edges, because they are really not needed in your minimum spanning tree, so obviously we'll have to remove them. The next step is to divide the vertices of the graph into two sets, visited set and unvisited set. So when you initialize it, since you haven't visited any set, it is null, and the unvisited set will be the set of all vertices. The next step is to pick any vertex, any arbitrary vertex. You can choose any of the vertices of the graph. You don't have to stick to one particular vertex. Any vertex as a starting point to generate the MST, and add it to the set V, because that particular vertex is already visited. You have chosen it to visit, so obviously you need to add it and you need to remove it from the unvisited set. The next step, in fact the most important step, is to find the least weighted edge among all the edges connected between the visited set and the unvisited set. So that's why it's greedy. So in this step we are picking only the least weighted edge that are connected from the unvisited vertices, from the visited vertices to unvisited vertices. We keep repeating this step, this fourth step, where we find the least weighted edge between the visited set and the unvisited set and add it to the MST, and accordingly we update the visited and unvisited sets also until all the vertices are visited. So we repeat this step until all the vertices are visited. This is a theoretical overview, so obviously it doesn't make most of the things clear. So an example would clear at least whatever doubts you have. So let's run through this algorithm with a graph. So here is a graph, the same graph which we used for Kruskal's algorithm. So you have all sorts of edges, loops, parallel edges, etc. So the first step is obviously to remove loops and parallel edges. We removed the loops and parallel edges. The next step is we need to choose an arbitrary node, any vertex. So we need to choose any particular vertex as our starting point. So in this case we've chosen A. So that is what we are that's where we want to start the generation of our minimum spanning tree. So we've chosen A. You can choose any other vertex for that matter. So now we updated the visited set to A because that's already visited. At least we began our journey from this vertex, so we added it to the visited set. The unvisited set is obviously the set of remaining vertices B, C, D, E, F. Now what is the next step? The next step is to consider all the edges that are connected from the visited set to unvisited set. That means we need to consider all the edges that are connected from the vertex A to B, C, D, E, F. So we need to find between from A to B, C, D, E, F. So you may not have all the edges. For example, in this case from A to B, C, D, E, F, ideally we need to have 5 edges, but in our graph we have only 4 edges from A to B, A to D, A to E and A to F. A to C is not there, there is no directed. So obviously we need to consider these 4 edges now. As you can see, these are the 4 edges that we consider, and we choose the best one among out of it. So what is the best one among out of these edges? So what is the best? Obviously AD is the least weighted wedge, so that should be added to the MST. We discard all the other edges. So we add AD. Now that we have added AD to the MST, D is also visited, so we need to add the vertex D to the visited set and remove it from the unvisited set. So this is the latest configuration. So we have added one edge and we have updated the visited and unvisited set. So this step is partially complete. I mean, at least we are done with the first iteration. Now this is where we are. Now we need to consider, because we haven't visited all the vertices, so we need to visit all the vertices, only then we can conclude the algorithm. So the next iteration, so we need to find all the edges connected from A and D to B, C, E and F. There may be several edges, so we need to consider all those edges. So these are the edges. So you have 6 edges and we need to choose the best among all of them. The best one is BD, because that is the one with the least weighted edge. So this is the least weighted one, because all the others have higher weights. So we add BD to the MST. Accordingly, we'll update the visited set to ADB and we remove B from the unvisited set. That's it. So we are done with this iteration. Now we need to consider all the edges connected from AD and B to CE and F. So these are the edges that we need to consider, because that's why these are highlighted in dotted edges, dotted lines. So we need to pick the best one. The best one in this case is 2, because all the others have higher weights. So we add BE to the MST. We discard all the others and we update the visited set to ADBE, because E is also visited now, and we remove it from unvisited set. We have CF. Now we need to consider edges from ADB and E to C and F. So we have these 4 edges. Out of these, this is the best one. So let us add it to the MST and update our visited and unvisited sets. So F is added and removed. F is added to the visited set and removed from the unvisited set, and the edge AF is added to the MST. So we are now left with only C, which is not yet visited. So we need to figure out how many edges are there, or what are the edges that are connected from A, D, B, E and F to C. There are only 2 edges, BC and DC, because all the other vertices are not directly connected to C. So we need to choose the better, the lesser value out of these 2 things, and 6 is the lesser one. So we consider BC and discard DC, and we update the visited set. Now that C is also visited, we add it to the visited set, and the unvisited set is empty. We don't have anything to visit. That's it, because that's what our algorithm, in the definition we've said that we can conclude the algorithm if all the vertices are visited. We have visited all the vertices, so we can conclude the algorithm. The final step is to generate the cost of the minimum spanning tree. It is 1 plus 2 plus 3 plus 5 plus 6, which is equal to 17. Basic question is, when do we stop this algorithm? We've already discussed that. So there are 2 ways. One way is to stop the algorithm when we have n minus 1 edges in the spanning tree if the number of vertices in the graph is n. So in this case we have 6 vertices, so obviously we can conclude it when we have 5 edges. There are 5 edges, as you can see, 1, 2, 4 and 5. So n minus 6 minus 1. So 5 edges. The other approach is, the other way to stop the algorithm is to ensure that all the edges, all the vertices are visited. Yes, we have visited all the vertices, the visited set is full, the unvisited set is empty. So that is another way to stop the algorithm. But the basic question here is, do we need to check for the cycles? Because that's what we used to do in Kruskal's algorithm. We had a separate approach called find union approach. We looked at it in fact. But do we need such kind of an approach here? Definitely not. Why don't we need that? The reason is pretty simple, pretty intuitive, pretty obvious as well. The reason is, we are always adding edges from the visited set to unvisited set. So if we consider the edges between the vertices of a visited set, then it is likely to form a cycle. But since we are considering only those edges which are connected from the visited set to unvisited set, obviously those edges will not add any cycle. You can probably work this out. You can check that for this particular graph. You can probably do it offline and then understand it in more detail. So the time complexity is again the mathematical part. So we need to find out all the combinations. Since we are dividing it into two sets and we are trying to find the number of combinations, that can be roughly calculated as V log V. The mathematical portion is skipped because that is not really within the purview of this particular session. So obviously we just need to have a basic overview of time complexity. So the number of combinations is in the order of V log V, and adding an edge to the MST takes, because there we are doing some activities, some operations like updating the visited set, unvisited set, and all those things. So that takes order of E. So together the time complexity can be amortized as order of E plus V log V. And this is the implementation part. So you can probably check this out. So this is uploaded in your Google Drive, the C program. So I've chosen the same graph, but you can update this graph. The adjacency matrix can be updated, and you can update the number of vertices here. The algorithm is defined here. A sample run is also given here. So this is the graph, and this is how the edges are added. So you can try this. You can take this program and then add whatever you want to add, or you can probably update your adjacency matrix and the number of vertices and then run this program. This is written in C. So the summary: finding minimum spanning tree using Prim's algorithm is also a greedy approach. So this also uses the same greedy approach what Kruskal's algorithm has done. The basic difference is it divides the vertices into visited and unvisited sets. This ensures that no cycle checking is needed. So since we are always finding the edges between visited and unvisited sets, cycle checking is really not necessary. Obviously it is not needed. Intuitively it is not needed. And we always add the least weighted edge among the ones connected between visited and unvisited sets. So that is what is written here. It eliminates the cycle checking because we are always finding the edges between visited nodes to unvisited nodes. And the time complexity of this algorithm is order of E plus V log V. And the final thing is that we have a quiz here, a 20-mark quiz. 10 marks, 10 questions will be there. So you can, it's a multiple choice questions. It's a multiple choice questions based test. So you can open this, you can give your email ID and then start answering it. It's open to everybody. So this is, you can try this quiz when you have time. Any questions can be answered. I mean, you can post your questions or you can directly call me on the mobile number that I've given. Thank you.